So welcome everybody to our Student Award talks. My name is Robin. I'm the president of the Color Research Society of Canada, and we are very happy today to have our two Student Award winners. Before we begin, I would like to just read our land acknowledgement that the CRSC's activities related to sharing color knowledge take place across Canada, understood as part of Turtle Island, the ancestral homelands of over 630 First Nation communities, representing more than 50 Indigenous nations and languages. We work to respect, affirm, and support, where necessary, the inherent treaty rights of all Indigenous peoples across these lands and waters. Our commitment to honoring the knowledge, ways of knowing, and wisdom of Turtle Island's Indigenous peoples aims to contribute to the decolonizing work required today for moving towards a just society. The CRSC is a nonprofit organization for color research focused on fostering a cross-disciplinary sharing of color knowledge. We seek to develop and support a national cross-disciplinary network of artists and designers, scholars, and practitioners with an interest and engagement in color. We like to encourage discourse between the arts, sciences, and industry, and related to color research and knowledge. We are the Canadian member organization of the AIC, International Color Association. So this evening, we're very happy to present our student awards. This year, we actually have two student award winners, joint awards at the graduate level. We will hear this evening from Carolina Espinoza-Sanhueza and Amitas Roshan. So this year, our jurors, thanks to them, were Dawn Dedrick, Julie Trudell, and Venkatamarananan. And we also very much would like to thank HAF2, who have generously supported the student awards for the last 3 years. So I will introduce our two speakers. We will have Carolina first and then Amita second. We're just going in alphabetical order. Carolina is a fourth year PhD student at Université Laval, and she is an architecture student. She will present her work on biophilic light and color for Northern architecture, conciliating occupants' well-being through responsive indoor colored ambiance. And then second, we will have Amitas Roshan. She defended successfully her thesis in March, so congratulations. She was at Simon Fraser University, and her advisor was our former board member, Brian Funt. And she is currently working for Apple in the Bay Area, so congratulations. And she will be telling us about metamer mismatching and its implications. So we'll start with Carolina. And yes, if everyone could mute, talks will be about 20 minutes, and then we'll have time for discussion, questions after, and then Amitas, we can have a larger discussion after your talk. So welcome again, and congratulations again for your winning the student awards this year. So Carolina, take it away.
Thank you very much. I'm going to try to share my screen. So. Okay, can you tell me if you see the presentation?
Yep, that looks good.
Great. Okay, before the presentation, I would like to say thank you for inviting me and to make me part of this Color Research Society. Today, I would like to present a part of my PhD, which is I give the title of Biophilic Light and Color Design in Extreme Latitudes. And when I say extreme latitudes, I would like to say what it comprehends all the Arctic and subarctic regions. And also the objective of this PhD project is to conciliate the northern occupants' well-being through biophilic, photobiological responsive indoor ambiances. I would like to also mention that this project makes part of a huge project at Laval University. We have an interdisciplinary knowledge transfer, so I would like to introduce a part of my committee, Claude Demers, which is a full professor at the School of Architecture, Marc Hébert, who is a full professor in neuroscience, and Jean-François Lalonde, our professor in electrical engineering. Before I would like to start, what is biophilia? And biophilia is the innate connection that people they have with nature. With nature, that means living beings, plants, air, colors, etc. But what we approach in this project is light. Why light? Is because it what show us the all the spatial configuration, but also it permits to know what are the conditions of the environmental the environment outside of the buildings. I always like to show at the beginning this this photo of the interior of the Pantheon, which is in a structure that with this opening could tell us what was the moment of the day, what time of the day it was, and also the conditions through the conditions of the sky, so we can know if it was cloudy or sunny, and with that we can the people they transform their life and they customize their way of living through the lighting conditions outside. And what before the use of the color, what it seems interesting, and also it makes a lot of it influences how we perceive light. It has its responsibility in the characterizing ambience. For example, in the first example, we see the National Assembly building in Dhaka, where we can see a very warm space and darker compared to the image below, just because of the color. And actually that was the color that was very in the surroundings, in the surroundings and in the landscape. So they construct all this building, and this influence in the way of living, the way how a color make part of the culture, make part of the ambience that the people inhabit, etc. Sometimes we think, okay, this is not very important, but actually it influences in some way in how these colors or the way of how we perceive the ambience can influence in the spatial experience. Before, also, we have the use of, since the day is composed by the day and night, we have also the use of artificial lighting. That before artificial lighting, it was only for the use of, for try to survive. I mean, they need light to eat, they need light to cook and make, prepare food, and also for conducting several activities, such as the image in the right, when we see this fashion merchant using this very tiny candle that I'm pretty sure it didn't illuminate the space as we see in the photo. Maybe the environment was dimmer. So the use of artificial lighting was used in a way to how to fulfill certain necessities to conduct our activities. But fulfill these necessities also create some ambiances, and we see all this this way to create ambiances just in the color of the painting. Sometimes we think, okay, this is not very important, this is not doesn't influence in our well-being, but actually it could influence in the way in regions where the light is gone, as we are going to see more in the north. And of course, it's going to influence in the special experience and in the perceptual well-being of the people. Right now, the use of lighting is completely different. We use it for not only for our daily life, for surviving, but it most to perform activities, as we see in the left image, where we have all these atelier that when we work with the students. And we see a combination of daylight, and actually we use electrical lighting to reinforce and to make our performance more, to activate actually our performance, to make it easy for writing, to make it easy for reading, etc. But there is another part of light that we use not only for perform, but it's most to create an ambience and to live experience. So our project concentrate in how to create ambiances that can be converted to fulfill specific activities, such as the writing or just work or just live, but also to fulfill other parts which is related with the perceptual aspects of light, but also in the photobiological needs that people they must to fulfill to trigger other biological processes that are fundamental for our body. The conditions of northern latitudes are really, really different to what we are used to live. I did an analysis of the hours of how many hours the people they will need to use electrical lighting, and there is almost a 42% of the year that the electrical lighting should be turned on just to give the minimum conditions, the minimum lighting conditions for vision, without taking in, without counting all the type of lighting that we need. I mean, the spectral light, the spectral properties of the light, because right now we know that we need lighting for enriched blue lighting for mornings, and we need like a more warm lighting for evenings. So there is a 42% that we need only for vision. And there is also another number that is very interesting, that the 77% of the year, the skies are cloudy, and it is very possible that it could influence in the lighting conditions in indoors. This is without counting all the time and the temperature that the people must rest inside of buildings just to make the activities, because normally outside is too cold. And if we see this image, and this is something that I would like to highlight, when you see this image, you see mostly a monochromatic ambience and landscape. So they have a very monochromatic ambience and landscape, but how is their conditions in indoors? So that is something that we are going to see after, but please keep with the idea that we have a 42% of the year that we don't have, that we have to use electrical lighting, and also the 22% of cloudy skies. And understanding this, how can we create ambiances to not only produce vision, but also to improve the biological processes of people in the northern regions. Right now, we know that what influences the conditions of the sky, the sun, the electrical lighting, and of course all the configuration. And we see that these all these conditions can produce the melatonin suppression during evenings, and of course induce the circadian clock reset during the mornings. And of course, something that we have to consider is the thresholds, because we know that vision and the lighting conditions to perform tasks are measured in lux, but right now what it influences in our retinal ganglion cells, which absorb this blue light, is measured in another metrics, which is melanopic eddy. And we know that, for example, for mornings, we need at least 136 melanopic eddy, and this value must decrease during evenings to induce people for sleeping. And of course, the circadian shift phase influence not only in the sleep and in the circadian synchronization, but it influences in the alertness states of the people, best coordination, even like in the best muscle tone, like at the moment that you need to make exercise, and of course in the quality of sleeping that of course affect the way that how the body rests and our performance in the next day, of course. So as you saw in one of the images that I showed you before, we are confronted with a complete photoperiod that affect the environment, and of course in a landscape that doesn't present any shade for most of the part of the year. But when we see the built environment in public buildings, we can see many saturated tonalities outside of the building, how you see in the image A, and also in the interiors. For example, the schools, the educational buildings are complete fulfill of saturated tones. Also in the university halls, that we can see how they add the red and the blue colors to improve the indoor conditions and to make it more stimulating for the community. But there is, of course, ancient buildings that are still present neutral tones, and the people they mention that they don't feel very how to say represented by this building. So we have this duality, and also we have the comments of the community when they say that they would like to have more colors to improve the indoors, where is the part that they perform most of their activities. And of course, they have this all these rituals made it with artificial lighting, in which they mark their traditions. It marks the return of the sun, and it creates an ambience what they make it feel like more comfy, and they remember their ancestors. So only with these examples, we can see color is a very important issue for public buildings, and of course lighting, which is in these images it's not electrical lighting, but at least is artificial lighting. It can improve the special experience of the community, whereas their education or their rituals. Also, we have work with the community, doing collaborative workshops in 2 times. It was in 2020 and 2022 after the pandemic. Well, you can see in some people, they are still using their mask in the images. Then we presented many projects to the elders, and actually they present a lot of interest in the images and in the projects that they some colors, they were integrated according to the landscape, according to the sunset and the sunrise. And I'm very happy to see, and I would like to give the credit to the students who work on this project. There were 2 winning projects in the Cote competition, AYA competition, where the people, they integrate colors that they found in the environment. Of course, the yellow colors are integrated in the sunrise, the blue in the sky, but also the red, despite the fact that we don't see many red in the landscape. The community, they show a lot of interest of this color because it makes a relation with the strong, with the muscular strength with animals. And in the project in the right, we can see how they integrate all these tonalities to simulate actually the sunrise and the sunset, which make it's a huge event after the polar night. So I would like to introduce this research question that I've been working on. Well, I know normally we work in a research question at the beginning of the research, but every time that we are understanding more and more the light and the color conditions in the Arctic, our research question is how we can provide many solutions to the community and what are the effects of these solutions, and also how can we conduct something that appear, and it makes me reflect all during the pandemic, how can we conduct research in the Arctic despite the fact that we cannot be there many times on the year, and going there is very costly. So what we do in this research actually is to propose light and color solutions according to the light Arctic light, I repeat 2 times the same word, according to the Arctic light photoperiod, and also how we propose a synthesis method of the effects of light and color to conduct at distance research. We know that we have to propose these solutions, but how can we simulate all the conditions in the Arctic, and how can we invite architects and designers to conduct research in the Arctic that can provide accurate results? So first, we've been working in a light and color characterization tool. That is the name that I give it at this moment. Maybe this name is going to change a little bit, but the idea is to reflect what are the visual and the non-visual effects of light. When I speak about visual effects, I like to speak about vision and the light intensity to perform tasks, like for example, reading, writing, etc. And the non-visual effects of light, which are related with the circadian stimulation, all the effects that doesn't produce an image in your brain, but it produces an image, an effect at the body level. And of course, how can we, and this is the very hard part, how we can predict some perceptual effects of light without working with people on site. So for that, we are working for light and color descriptors that, despite the fact they don't produce a solution or a response about how a person can experience a space, we can describe a space and we can say, okay, this space is very bright, it's very vivid, so maybe it could be stimulating for the community. So I don't want you to read all this this information, but this is an example of how we can enter results. For example, vertical luminance at 300 lux, and we can use we could use a scene for all these activities and architectural programming, for example, for restaurants, for living rooms, for an office for reading and writing, for handwritten work, etc. And also we make a relation of how, what means this equivalent melanopic illuminance looks, which is what produced this effect, the threshold for the photobiological processes at the circadian level in our body. Sometimes we explain to the students what means a threshold, but they don't understand very well for what we can be, for what can we do with this threshold. So we synthesize all this information to say just recommended for mornings, recommended for evenings, etc., etc. Another part of the also about the colors is how what a color palette of an ambience can tell to us. So right now, for example, just with this example, I can say like this ambience is a very cold ambience because the majority of the color, the points of the color palette is just in the cold area of the color wheel. We see that the CCC, the correlated color temperature of the scene is at 6,000, which is very cold. And also we can see that the ambience that we have studied, it's that like it has some points according to the saturation and the brightening properties. It's very vivid, it's saturated, it's intense, it could be very dark. So this can give us some clues about how is the lighting conditions of each ambience that we are analyzing. And of course, the brightness contrast, which is also, it doesn't give us, it doesn't speak about the experience, but we can predict, for example, some states of concentration, distraction. Also, we can measure the distribution brightness map of an ambience. We can see how much dark is in each scene that we are studying, etc. So as the other part is to understand the color solutions and the light and color solutions, and for that we wanted to study the effects under daylight and electrical lighting. And in this case of daylight, we have used a mirror box artificial sky simulation, which simulates actually the same conditions of real sky. We have a sky at very warm color temperature, which our artificial sky provide us the same color temperature of the ambience, or to other color temperature very high at 6,500, and we could simulate these conditions. That of course is going to change the indoor condition of each ambience that we were studying. We have used 4 main colors, and we base these 4 main colors as in the CIE CIELAB color system from the CIA, the Commission Internationale de l'Éclairage. And also we have used different color configuration surfaces. Like we have add some colors in floor, in the ceiling, and what our result says is like many, there is an effects of the some effects about the property of the finishing. It could be glossy, it could be matte, and also some effects in the reflectance of in the color reflectance of each scene. We can see that, for example, yellow is very reflective, very reflective. It produces a lot of EML, but the color temperature of the ambience is very warm. So we can induce, for example, circadian stimulation, but produce a very cozy ambience or and I know, for example, in this case, we have used only main tonalities, but when we work with the chroma, the saturation, the brightness, we could construct a more comfortable ambience that the people will feel more cozy, or it could induce their well-being. And the other part is the analysis of the intensity contrast, and we see how the color position, of course, influence in the dark distribution of the ambience, but also it gives the visual effect that, for example, the windows can be enlarged, and of course it could be influenced in some way in the perception of the space and in the how do we feel in indoors. The other part, and I want to go quick because I think I already passed my
Yeah, I think about 2 minutes.
Okay, I'm gonna finish.
2 or 3 minutes, yeah.
Yeah, so the other part is the electrical lighting. We have used 8 color concepts, and we have construct a reduced scale model. Is a prototype that permits to change very easily the variables. So we have changed the variables of color, we have changed the variables of lighting strategy, and of course the CCT from very warm, white, and from cool lighting. And then that is what we had in indoors. That is what our prototype was used. We change all the parameters inside, and that is what we capture. We control this Raspberry Pi, which is a remote camera from just beside the model to avoid any handling, and also we change the color temperature using a hue Bluetooth application that permits to change all the conditions inside without moving anything that we had in indoors. So this is an overview of what we have produced, and this, of course, what it changed is, of course, the color palette, because the lighting doesn't enter in the same way it doesn't touch all the surfaces in the same way, which can help us to change the perception of the colors inside, and of course it could help to change the photobiological effects in terms of light intensity and circadian stimulation. We can see that, for example, some spaces can produce same color scene can produce very different levels according to photopic illuminance and melanopicity. And of course, for example, here we see that only the change in the section 2 here in this place, we can see how a semi-space can be used for the same activities, but they don't produce the same circadian stimulation. Another example is we can see how 4 different settings of color can produce the same circadian stimulation. So this opens up the possibilities to for the use of color and for the use of color to augment physiological well-being in people in the north. And what I would like to retain is that biophilic design could benefit occupants in the northern architecture. It's important to consider the climate challenges and the photoperiod. And it's, of course, what I would like to, I state that light and color benefits the occupants of the north, and it could improve architecture. And that I mentioned that different light and color scenes could produce similar visual and non-visual effects. And I would like to invite architects and designers to conduct studies in northern latitudes and combine analogical and new technologies such as photocalibration and images and photography to improve these occupants' well-being. So thank you very much, and thank you for participating in this presentation.
Thank you so much, Carolina. That was fantastic. Very important work. We'll take one or two questions. If anyone wants to just put your camera on and you can unmute or put your hand up.
Hi, yeah, no, thank you. It's an interesting talk. I wondered, you talked about the color temperature a lot, but do you take into account the spectra? Because I mean, you can get, fluorescent lights that give you 6,500, but they're spiky spectra, and this really could make a difference, I imagine. Do you think about that kind of stuff?
When we calculate actually correlated color temperature, but we calculate it from the light source, we use an spectrometer, and actually it doesn't, the light system doesn't have the same spectra of the sky, because it has this peak in the blue portion because it's LED. But in each scene, what we did to calculate the CCT was using a HDR images and photo calibrating with the RGB peaks with the eye sensitivity.
I understand. Okay, I understand that, but if you have something that's 6,500, there are all these different ways to make it, and some of them are more like daylight, which is they're really a smooth spectrum, and others are just all, a spike here and a spike here and a spike there. And this could make a difference, I think, in terms of how the colors show up and even perhaps the melanopsin. I'm just saying, it's important not to just, to me, it would seem important just to not think about color temperature only, but rather the how equivalent it is to the daylight. So you want to make 6,500, that's like a 6,500 spectrum, not just that something that's the same color.
Yeah, I know what you mean, but actually that is one of the limitation of our equipment, that we can match the correlated color temperature, and for this system we use white LEDs, but of course we cannot simulate the same spectral conditions, but it helps a lot for professional practice and also for education. So that is something that it's very interesting to us, how to introduce students and architects that here in Quebec they produce a lot of research for the North, but how can we match all these conditions for the North? That is something that it continues to be very challenging for our research project.
Okay, thank you.
Thank you, Montaha. You have a question?
Yeah, thank you, Carolina. That was really very interesting. I have two questions. The first one, you talked about the results of your study basically showed that some colors, or I understood some colors, benefit the circadian well-being system. And so they are beneficial, let's say, to the human being. And so in the northern latitudes. So I was wondering what were those colors and whether or not the chromaticness of the colors plays an effect, like were they pale colors or very saturated colors, etc. And the second question is in the model that you showed the pictures, there was inside the model, there was always an illuminated square on the top. What was that square representing? Was that the light source or was it something else?
Yeah, for the first question, actually there is some colors that they could because color is subjective and color preference is also subjective, it changes between people and communities. But if we talk about circadian synchronization, we know that blue light color, it could be more beneficial for circadian synchronization, but there is also an important factor that before people they didn't take into account, but actually is very important, is intensity of light. So I can have, for example, a CCT of 4,000 Kelvin, and if its intensity is very high, it's going to also induce circadian synchronization. What I think it's important of this research and of this study is that very many color design concepts in the how to say in the indoor environment can produce similar circadian stimulation, because what it changes is the reflectance of the surfaces, is the intensity of light, is the light position. So this opened the possibilities to use color because before it was all the people, they say, no, okay, a blue lamp, it's going to produce a lot of circadian stimulation. In some way, yes, but actually the intensity and the conditions of the surfaces is also an important variable. And about the second question, when you mean the square, it's like the photo of the point of view of the observer?
Yeah, well, you always showed the picture of the model inside the model with the walls and the ceiling and the ground. But on the ceiling part, there was always a square that was illuminated. So I was wondering if that was like the light source, or was it something else?
Yeah, that was the light source and the way how we simulate the light source. As I mentioned, we use many, this research is also focused in education in professional practice. So we want to approach methods that is very easy for architects, which means scale models. So it's because of that using something very crafty, very analogical, we could produce very reliable results, because we have extract a technique from a verified technique to match the color functions of an image with the same sensitivity of the eye. Of course, there are some limitations. I think we have a 90% of accuracy of our research, but what we want to highlight of this study is the different methods to how to approach, for example, neuroscience or biological processes of the human body into architecture. Because sometimes that is something that the architects, they don't take into account. They are very into the design and the form, but architecture influence in many ways in the well-being of the humans. And actually a lot, especially in the north, the people, they spend a lot of time indoors.
Okay, thank you so much, Carolina.
Thank you so much. Thank you for your questions, and congratulations again, Carolina, and thank you for this work. It's very interesting and very important work. Thank you for sharing. I'd like to turn the floor screen over to Ambiances. Do you want to bring your camera up and tell us about your project on metamer mismatching and its implications?
Sure. I booked this room for, till 5, and I hope no one shows up, otherwise I have to.
Sorry.
It's okay, let's just hope. Okay. So can you see this right now?
Everything's good, thank you.
Okay. So hello everyone, my name is Ambiances, and I worked on my PhD under the supervision of Dr. Brian Flan at Simon Fraser University. The the topic of my thesis is metamer mismatching and its implications. So first I explain about the metamer mismatching phenomenon, and then I explain about the topics and problems that exist in color science that we use actually the metamer mismatching concept to tackle those problems. Metamer mismatching. Despite common usage, color is not an intrinsic property of an object. This is the key point of this presentation. So I want to ask you to please pay attention to this. Color is not an intrinsic property of an object. If you look at the image on the left, you see two balls placed in a light booth. The material that the balls are made of are different. So the reflectance functions of these two balls are different. But you see those two balls under the same light, the colors of those two balls, they look the same. But so they both are like orange. But when we bring them under a different light, if you look at the image on the right, you see that when you change the light, the color has changed. So color is not an intrinsic property of an object. It's actually the reflectance that is an intrinsic feature of an object. So when the two balls at the left, their color match, it's called metamer. So the two balls are metamer, but when we bring them under a different light, their color may mismatch. This is called metamer mismatching. But what is a reflectance function? So when we lit an object with a light source, different things may happen. Part of the light can be like absorbed, part of it maybe like may pass through the object if it's like transparent like glass, but part of it may be like reflected. This is the reflection is what we care about, and this is the thing that allows us to see the object, the light that is reflected from the object. But how it or how much it will be reflected, this is something that is called reflectance function. So we are all familiar with two extreme cases, like a white surface and a black surface. So at the top, you see the white surface actually reflects like 100% of the light, the incident light. And that's why you see it as white. And the black surface, on the other hand, it reflects like 0% of the incident light. So that is why we see it's black. We don't see any color. And so these are just two extreme cases, but for other objects, like in our example, the red flower here, the reflectance function shows that it shows the wavelength composition of the reflected light, and it shows like what is the percentage of the incident light that is reflected off the surface. So for example, for the red flower here, we see an example that a small portion of the small percentage of the incident light near the short wavelengths are reflected, and a higher percentage for the like long wavelengths part is reflected. But how the reflectance function is related to color signal? Our eye has 3 photoreceptors known as cone cells. Each type of these cone cells are sensitive to part of the spectrum. For example, the S cones are they're called S cones because they are more sensitive around the short wavelengths part of the spectrum, and we have the medium and long. And based on the you see the equation of color signal. This is how the light, the combination of the incident light, the reflectance function of an object, and the spectral sensitivity of the sensor, that can be like our cone cells, human cone cells, or can be the sensitivities of the like camera sensors. The combination of these actually generate the color signal. And when I say color signal, I mean the RGB of the camera, XYZ, any color coordinate, Mansell or NCS color coordinates. So it's you don't have to be worried about the details of this equation, but it's almost like clear from this equation that if you change for a given object with a given reflectance function, if you change the light or the sensor changes, the color signal may change. So again, back to metamer mismatching. So here we see an example, the 2 cups with different spectral reflectance functions. They produce the same color signal under D65 daylight. And in this case, they are called metamer. But when we bring them under a different light, let's say tungsten light, they do not match anymore. So this is called illuminant-induced metamer mismatching. We also have observer-induced metamer mismatching. So let's say in our example here, we have two cups at the top. If we capture an image with a given camera, the RGB of two cups that have different reflectance function, they may match. So they are metamer with respect to that camera. But if we capture an image with a different camera or we compute the color signal with the human cones, they may mismatch. So this is called observer-induced metamer mismatching. So as we saw before, any change in light or sensor can cause the color signal to change. So we refer to the combination of light and sensor as the color mechanism. Let's say we are given an object with a reflectance function, and the color signal of this object with respect to a first color mechanism is color signal 1. If we gather all the reflectance functions, all the objects in the world that produce the same color signal with respect to the first color mechanism, and if we compute their color with respect to a second color mechanism, the color signals, the RGB or the XYZ of all these objects that were metamer with respect to the first color mechanism, their RGBs under the second color mechanism, they form a convex body that is known as metamer mismatch body, or MMB. There is another concept that I need to talk about here. OCS is simply all the color signal, all the possible RGB or XYZ that can occur with a given color mechanism. And it has been proven that it's a convex volume. So it's like if you have a light and sensor, if you gather all the existing objects in the world and you compute their color signal, OCS shows it's a convex hull that shows what colors can be generated with those lights and combination of those lights and sensor. So here is an example. The big gray object here, it shows the OCS under D65 daylight. So this is a 3D object that each point within this object, it represents a color signal that is generated by like a bunch of materials. Here we also have the OCS under tungsten light, which is different from the OCS, the colors that are generated under D65 daylight. So if you have a like a gray paper and you compute the XYZ of that gray paper under the tungsten light, it will be this black circle. If you gather all the objects, all the reflectance functions that are metamer to this gray paper under tungsten light, and then you compute their color signal under the D65 daylight, this is it forms this body which is known as MMB. So the first topic that I used MMB for, accuracy of digital cameras. We all know that the cameras are not designed for to be used as an imaging colorimeter. Cameras are usually designed to capture good-looking images, pleasing images. But and we know that there are some limitations in designing cameras, like the cost, physical limitation, noise, and all those can cause the color accuracy to be sacrificed. But despite this fact, we know that it has become very common to use our cell phone cameras as imaging colorimeters because of image quality, portability, and affordability. But we should keep in mind that it's risky because we saw that if the light changes or the sensor changes, then the color can change. So using different cameras, uncontrolled camera, uncontrolled light, and we don't have any control on the light. So the color that they measure can be different. Anyway, it has become very common to use our cell phone. So how can we say if it's accurate or not? We know that color is accurate color is very important in different fields. Like color is one of the main elements in early diagnosis of cancer or dental disorders or ophthalmology or dermatological, many different diseases. Color is widely being used in medical tests like anemia, pH 14, or glucose test. Or it has become very common to use color in intelligent agriculture or many different fields. So how can we say that if a camera is accurate or not in terms of color? Luther condition says that if camera sensitivity functions are directly related to the human cones, then it's perfectly accurate. So we proposed a measure based on metamer mismatching between given camera and cones. But what is the intuition behind that? We actually know that they never are. They never can, no camera can satisfy this condition. So how can we rank them? How can we say which one is better than the other? We propose a metric based on the data of metamer mismatching. The intuition behind using this is that if a human observer sees two objects as the same, we want the camera to see them as the same color too, and vice versa. And if that's not the case, let's say a camera sees two objects as the same color. Here is an example. You can see the camera measures the same RGB for these two patches, but human sees them as different. So the greater the difference, the poorer the colorimetric accuracy. And this is related to metamer mismatching, right? The two patches are metamer with respect to camera, but they mismatch under with respect to human cones. So we propose to use the volume of metamer mismatching. I mean, we could use the volume of the metamer mismatch body as a measure, but the problem that one problem that comes up with the volume is that, as you can see in this plot, the MMB can be very thin for some cases, and when it's thin, the volume can be near zero, even though the metamer mismatching is large. So we, instead of using the volume, we propose to use the shape. So we proposed a measure called CMMRI, or camera metamer mismatch radii index, that measures the shape of the MMB rather than its volume. And the smaller the MMB, the better. That's as you saw in the previous plot, the MMBs are like a wing-like shape, and so it's not straightforward to measure the shape, but I'm not going to bother you with the details how we introduce an algorithm to measure the shape. So we use our method and we took some of the cameras that exist in the market, and we ranked them using this method. And like one of the takeaway from this plot is that, for example, Canon cameras are, because we said the smaller the better, smaller MMB. So based on this plot, for example, Canon cameras are doing on average better than like Nikon cameras. So to summarize, we introduced a color accuracy metric for digital cameras based on the digraph metamer mismatching. We propose to use its shape instead of its volume. And the metric that we introduced, it's actually independent of any linear transformation that might be applied to the sensor space. And it measures how much error can arise in principle. It's not unlike the existing metric, it doesn't measure an average error over a sample set. The problem with that is that if you change the sample set, the average error may change, and then the ranking may change. So ours is the proposed metric is robust with regard to that. So the next topic is color discrimination theory. McAdam in 1942, he conducted an experiment. He showed pairs of colors to people and asked them if they look the same or not. And then he gathered the data set and he fitted ellipses to those colors. So ellipses in this plot, it shows the region of color. So each point within this region is not distinguishable from the center of the ellipsoid. Actually, the ellipsoids, the original ellipsoids are smaller. They I just plotted it this way. We scaled them just for visualization purpose. So you can see that for some parts of the color space or the chromaticity plane here, the ellipses are bigger than the others. Why? But what is the reason? People repeated similar experiments and they measured the discrimination ellipsoids in 3D color spaces, but no one actually explained what is the underlying reason. we propose the theory that it's due to metamer mismatching. Zhang et al., they measured the MMB volume or different colors, and they showed that actually MMB is the biggest near gray, and it gets smaller when we go toward the saturated color. And we saw an inverse relationship, I mean, an inverse trend for color discrimination. So we are going to be, the theory is that the bigger the MMB, the larger is and more varied is the set of reflectances that are all metameric to that color. So there is more uncertainty as to the exact nature of the underlying surface reflectance function. So for a human observer to be able to reliably discriminate physically distinct surfaces, the human observer must be more sensitive to those colors for which the metamer mismatching creates significant uncertainty. So in a very simple word, when we have a big, if for a given color signal, we have a bigger MMV, it means that there are more number of objects that can create that color signal. So we should be more sensitive. And then the color discrimination, because we get more sensitive, the color discrimination is smaller around that color. So we gathered the some data sets, the existing data set that we found, and we ran a statistical test. And the result of the statistical test showed that there is not enough evidence to reject this hypothesis. We actually compared our proposed model with existing uniform color spaces. So, for example, CAM16 UCS is one of the most uniform existing color space that actually its parameter is, the parameters are optimized to fit the experimental data. But even though that it's a fit to the data, you can see that its prediction of the discrimination ellipsoid is very comparable with ours. So this is on the left, you see our prediction, and on the right, you see CAM16 UCS prediction of the experimental ellipsoid. So as a summary, we proposed a color accuracy metric based on degree of metamer mismatching. The proposed metric measures how much error can arise in principle. It's rather than just taking average over a sample set. We propose a hypothesis about color discrimination that the uncertainty due to metamer mismatching is the underlying factor of the variation in color discrimination threshold. And we showed that CAM models that are based on parameter fits to psychophysical data are not better predictor. We also used it for the metamer mismatching concept for another topic, but I skipped it because of time limitation. I decided to not talk about it. Yeah, any question?
Thank you so much, Amita. That was very interesting.
Thank you.
Would anyone like to ask any questions? Do you want to unshare your screen? And
Sure.
People can.
Excellent research, and this, thank you.
Thank you.
Yeah, I would like to say the same. I think I'm less, I understand a little bit less about the topic, but it sounds very interesting and actually for the applications, actually. Yeah.
Yeah, I'm very
Thank you so much.
knowledgeable of metamerism, and I used to work a lot with metamerism and powder coating. So I'm glad that a student did a study about metamers.
Thank you.
Are there any applications that might use your model, like you showed the looking at skin tone or looking at cancer diagnostic? Have you had any contacts with any specific applications for your model?
Application, Actually, it measures the accuracy of the camera, right? So we can, in designing the sensor, I mean, like there are some limitations because of the fabrication process, but before that, when you are deciding what should be the shape of the sensitivities, spectral sensitivities of the sensor, you can use this to design the most accurate one, and later, when you're going to, for example, make a cell phone, you have to decide, instead of just buying the sensor and then trying to make it accurate, you can decide beforehand to buy a sensor that can be more accurate in terms of color. And yeah.
And your models are able to better predict the best sensors for.
Yes.
Mm.
I can say that, well, yeah, this is an accuracy metric, so it can measure how much error can happen actually later, can be predicted.
Are there differences in the colors, like, or the wavelengths? I find often reds are not as well captured by cameras as opposed to the eye. Like, do you find that there's any systematic change?
Well, yeah, that's of course there are some variation between like different human cones, like from like between different like observers. They are not exactly the same. So there are the red that you see, the perceived color it can be different from what I perceive, right? But to be able to make it closer to the average observer, that's something that can help. Yeah, but anyway, at the end there will be some variation, and it's very difficult to make it like perfectly exactly similar to what you perceive, but it can help to make it closer to the average observer.
Any other questions? Sarah had a question for Carolina. I think and also what you said at the very beginning, that, you know, color is not a property of an object. It's the perception and the fact that there are all these things that go into the perceiver. And Sarah pointed out that, you know, there might be vast cultural differences in color to Carolina, and just wondered how that might play a role in the work that you're doing.
Yes, actually, the main differences of colors is the way how they named color, but I mean name the colors many years ago, because right now, this is related with the second question. At this moment, the community, we are working with a specific community in Cambridge Bay Nunavut, and it's about 2,000 people there. And I think most of the community, they have lost their language, and the people who they continue speaking this language is elders, but actually they don't make a huge part of the community. So every time that we have these meetings and workshops, we have translators, and also we understand that the colors, something very interesting about the community is like the colors they mostly highlight in their preferences is related with the sunrise and the sunset. And so it's in the way they describe the color, at least they can use general descriptors and general adjectives for that. For example, saturated, bright, very bright, very dark. At that point, it's not a huge problem. But I think when we have this kind of limitation is with the elders. But contact research with elders, just having a meeting with them is very difficult because they are very, very, very protected. So all the outcomes that we have with in the collaborative workshops, we cannot use it for research. We can just use it to have clues where to try to find out some information. But it cannot be for publishing. We cannot use sometimes it can be very not useful for the research, but I think it's an experience that we keep with them and between the community and the students.
Yeah, so fascinating. All these different dimensions to color, and themes that kind of brings them all together, and it's just highlights how complicated color is. All right. Well, thank you so much, Carolina and Amitas, and congratulations again. And we very much enjoyed your talks. Yes, this session is being recorded, and we will let you know when it's ready on our webpage. Yes, so please, everybody, clap virtually or and thank you once again. And thank you, everybody, for joining us.
Thank you very much. Thank you.
Thank you for the opportunity.
Yes.
Thank you.
Thank you. Congratulations again.
All right. And stay tuned to our website. We are going to keep on keeping on with these talks, and we'll let you know our plans for the next kind of 6 months. We'll send out newsletters and keep you posted. So thanks, everyone.
Thank you.
Bye.
Bye.
Bye-bye.
Bye.